Paris's most famous iron tower grows 15 centimeters taller every summer. Stand on the Champ de Mars in July. The Eiffel Tower looks identical to January. Same iron, same shape, same rivets, but if you slapped a precise measuring tool on it, you'd catch something weird. The tower in front of you is taller than it was 6 months ago. Not by much, 15 centimeters. But it's real. 15 centimeters on a 330-meter structure. That's less than 0.5%, but it's not a rounding error. It's not an illusion. It's a measurable, predictable change in one of the most photographed objects on Earth. And the cause? Heat, something you deal with every single day. Here's how it works. Every metal object near you is atoms arranged in a grid. Heat that metal and you're adding energy. The atoms vibrate harder, they jostle, they shove against each other. And when atoms push apart, the material has to get bigger. All of it, every direction. This is thermal expansion. Every solid does it, but metals are especially good at it because their atomic bonds are uniform. Iron's coefficient of thermal expansion is about 12 parts per million per degree Celsius. Sounds tiny, but multiply it across 330 meters and a 40-degree temperature swing. You get 15 centimeters. Let's get concrete. Heat a 1-meter iron bar by 1 degree. It grows about 12 microns. You'd never notice. But the Eiffel Tower isn't 1 meter. It's 330. And Paris in summer isn't 1 degree warmer than winter. It can be 40 degrees warmer. 12 microns times 330 times 40. Simple math, 15 centimeters. The equation is basic. Change in length equals original length times the expansion coefficient times temperature change. 3 numbers multiplied. But here's what's wild. Every iron structure on Earth, from a nail to a bridge to a tower, obeys this equation constantly. No off switch. Now here's where the Eiffel Tower gets more interesting. The sun doesn't heat all sides equally. Morning hits the east face first. By afternoon, the south side is fully exposed. One side is always warmer than the other. The warmer side expands more, so the tower doesn't just grow, it bends. The top actually tilts. It leans away from the sun because the sunlit side is longer than the shadowed side. The shift can hit 18 centimeters from true vertical. Tourists at the top never feel it. The curve is too gradual across 330 meters, but instruments track it. Every clear day, the top swings in a small arc, following the sun. Think about that. The top of the Eiffel Tower traces a daily path. Morning, it leans west. Noon, it leans north or south depending on the season. Evening, it leans east. A slow, silent pendulum driven not by gravity but by photons. The sun pushes the tower with light, not the force of light. The heat of light, and the iron responds. Gustave Eiffel knew this would happen. He wasn't surprised. He was a man of extraordinary precision, a bridge builder before he built towers. He understood thermal expansion intimately. He'd been designing metal structures for decades. When he planned the tower for the 1889 World's Fair, he accounted for all of this. The entire structure was designed to move. The tower is 18,000 individual iron pieces held together by 2.5 million rivets. Rivets aren't welds. They're mechanical fasteners that allow a tiny bit of give between pieces. Partly a construction convenience, but it also means the tower has built-in flexibility. One section expands, the rivets let neighboring sections shift. The whole structure breathes without cracking. The iron is a specific type called puddled iron. The process removes impurities and creates a remarkably uniform material. Eiffel used about 7,300 tons of it. Total weight of the tower, including non-iron components, is around 10,100 tons. Every gram responds to temperature. Every gram expands in summer, contracts in winter. So here's the natural question. If thermal expansion is this powerful, what happens to structures that aren't designed for it? They fail. Railroad tracks are the classic example. Steel rails are laid in segments with small gaps between them. Those gaps are expansion joints. On a hot day, each rail segment grows and the gaps close. If the gaps are too small, the rails have nowhere to go. They buckle. Track buckling is a real and dangerous problem. During heat waves, rail networks worldwide issue speed restrictions because buckled tracks derail trains. The iron literally bends sideways under its own expansion pressure. In the UK in 2018, a heat wave caused dozens of track buckles in a single week. Engineers paint rails white in extreme heat to reflect sunlight and drop the temperature. The Eiffel Tower never buckles. Its lattice design spreads expansion across thousands of joints. Bridges face the same challenge. The Golden Gate Bridge in San Francisco can swing more than 4 meters sideways in high wind, but it also moves with temperature. Its main cables, over 2 kilometers long, expand and contract every season. Bridge designers build expansion joints into the deck. Without them, a hot day would literally tear the bridge apart from within. The forces are that large. And it's not just big structures. The power lines outside your window sag lower in summer than in winter. If they were strung tight in July, they'd snap in January when the metal contracted. So utility companies hang them with calculated slack. Summer, the slack decreases as wires expand. Winter, the lines pull taut. You've probably seen this your whole life without realizing you were watching thermal expansion. Even the lid on a jar of pickles works on this principle. Run it under hot water. The metal lid expands slightly more than the glass jar. The seal breaks. You've used thermal expansion to open jars dozens of times. You just didn't name it. The same physics that lifts the Eiffel Tower 15 centimeters also gets you to your pickles. But here's what makes the Eiffel Tower special. It's not that it expands. Everything expands. It's that the expansion is so perfectly predictable and so gracefully accommodated that the structure feels alive. Modern GPS receivers mounted on the tower measure its height to within a few millimeters. They confirm what the math predicts. August, the tower is tallest. February, it's shortest, consistent year after year. The cycle is like breathing. March to August, the tower inhales. It grows slowly day by day as Paris warms. September to February, it exhales. It settles back down, centimeter by centimeter, as the cold returns. By midwinter, the tower is about 15 centimeters shorter than its summer peak. Then the days lengthen, the iron warms, and it starts again. It's been doing this for 135 years. The tower was completed in 1889. It has breathed in and out roughly 135 times. 135 summers of growth. 135 winters of contraction. No maintenance, no adjustment, no mechanical system. Just iron responding to the sun, exactly as Gustave Eiffel calculated. Think about that longevity. Most machines need active systems to manage thermal expansion. Engines have cooling systems. Pipelines have expansion loops. Skyscrapers have expansion joints in their steel frames. The Eiffel Tower manages it passively, through geometry and material choice. The lattice shape distributes expansion evenly instead of concentrating at any weak point. The puddled iron is uniform enough that no section behaves differently from its neighbors. Eiffel himself wrote about this. He noted the structure was designed to withstand wind, which was the public's primary fear. But he also understood thermal effects deeply. He'd spent years designing iron bridges for the French railway system, where thermal expansion was a daily engineering reality. The tower was, in a sense, the largest bridge he ever built. A bridge to nowhere, standing still, but engineered with the same principles. The numbers are worth pausing on. A 15-centimeter height change means the top moves through a range longer than a standard ruler. The 18-centimeter tilt means the top shifts sideways by roughly the width of a large book. These aren't trivial movements. If you scaled the tower down to human height, the proportional change would be like a person growing and shrinking a few millimeters every day. You'd notice if someone did that. And the tower isn't alone. Every iron structure, every steel frame, every metal bridge is doing the same thing right now. The chair you're sitting on, if it has metal legs, is slightly taller in a warm room than a cold one. The change is microscopic, but it's there. The Eiffel Tower just makes the invisible visible. Because it's large enough that invisible becomes measurable, and measurable becomes astonishing. There's a philosophical edge here. We think of metal as the most rigid, unchanging material. Stone erodes, wood rots, plastic melts, but metal, we imagine, is solid and permanent. The truth is metal is the most responsive material we have. It reacts to temperature faster and more dramatically than almost anything else. It just does it silently, within limits, so we never notice. The Eiffel Tower is, in a quiet way, the largest thermometer in the world. You can't read it with your eyes, but if you had a precise enough ruler and a ladder tall enough, you could walk up, measure, and know the temperature of Paris to within a degree or two. The tower is recording the weather in its own body, in real time, through the language of molecular spacing. This is what makes thermal expansion beautiful, not just useful. The same physics that buckles train tracks and loosens jar lids also makes one of the world's most beloved structures rise and fall with the seasons. The tower doesn't just stand in Paris, it participates in Paris. It absorbs the city's summers and winters, and translates them into a slow, vertical dance that no tourist ever sees, but every instrument can confirm. Gustave Eiffel died in 1923, 34 years after his tower was completed. He never saw GPS confirm his calculations. He never saw modern sensors measure the daily pendulum of the tower's summit. But he didn't need to. He'd done the math by hand, with slide rules and drafting tables, and he trusted it. The tower has proven him right every single day for over a century. So next time you see a photo of the Eiffel Tower in summer, remember what you're looking at isn't static. It's a structure in the middle of a slow, invisible stretch. The iron atoms are vibrating harder than they were in January. The lattice is slightly wider. The rivets are slightly more stressed. The top is leaning a few centimeters away from the sun. And in 6 months, all of it reverses. Metal breathes, we just never think to listen. The Eiffel Tower proves it does, and that the breathing has been going on, steadily and silently, since before your grandparents were born. Every summer it grows. Every winter it shrinks. Every year it does it again. 15 centimeters, up and down. Up and down. A 10,000-ton iron lung, standing in the center of Paris, breathing with the planet. Follow for more strange facts hiding in plain sight.